From a tiny cut on your finger to a full-blown flu infection to bizarre autoimmune diseases where your body attacks itself, this is how your immune system actually fights infections. And spoiler, some immune responses happen in seconds, others take days to activate, and a few involve your own cells essentially committing suicide to protect you. Right now, billions of bacteria are trying to invade your body through your skin, your mouth, your nose. Most of them fail. But the ones that get through, that's when the real war begins. We're talking trillions of microbes versus an army of specialized killer cells, each with one job: destroy the invader before it destroys you. And the craziest part? This entire battle happens automatically, without you thinking about it once. But first, let's start at the beginning. What actually happens when you get a paper cut? Right now, as you're reading this, your skin is under attack. Billions of bacteria are trying to break through. Viruses are attempting to slip past your defenses. Fungi are looking for any tiny opening they can exploit. And most of the time, they fail. Your skin is basically a fortress. The outermost layer is made of dead cells packed so tightly together that most microbes can't squeeze through. It's like trying to break into a building with walls made of bricks, except each brick is a dead cell, and there are about 20 layers of them stacked on top of each other. That's 2 square meters of protective barrier, about the size of a beach towel, covering your entire body. But it's not just a physical wall. Your skin also produces oils and sweat that create a slightly acidic environment with a pH around 5.5. Most bacteria hate that. They prefer neutral or alkaline conditions, so your skin is basically coated in a chemical weapon that says, "Stay out." And then there's your microbiome. Right now, you have about 100 trillion microbes living on your body. That's more than the number of your own cells. But here's the thing. Most of them are on your side. These good bacteria occupy all the prime real estate on your skin, which means when bad bacteria show up, there's literally no room for them. It's like every seat at the restaurant is already taken. Your nose and throat have their own defense system, mucus. That sticky, gross stuff traps bacteria and viruses before they can reach your lungs. Then tiny hair-like structures called cilia sweep the mucus up and out, or down into your stomach where the real violence happens. Your stomach acid sits at a pH between 1.5 and 3.5. That's battery acid levels. It dissolves food, sure, but it also obliterates most bacteria, viruses, and parasites unlucky enough to make it that far. We're talking about a chemical environment so hostile that only the toughest microbes survive. Every time you touch a doorknob, shake hands, or breathe, you're exposing yourself to thousands of potential threats. Most never make it past these first defenses. Your body handles them automatically, without you ever knowing they were there. But sometimes the barriers fail. A cut, a scrape, a wound that breaks the skin. Even something as small as a paper cut creates a breach about a millimeter wide. So what happens the instant that barrier breaks? The second your skin breaks, an alarm goes off. You know that red, hot, swollen feeling around a cut? That's not infection, that's your immune system going to war. Within seconds of the injury, damaged cells release chemical signals called cytokines. Think of them as emergency flares. These signals tell nearby blood vessels to dilate, which means they get wider. More blood flows to the area, which is why it turns red. The extra blood brings heat, which is why the cut feels warm. And as the blood vessels expand, fluid leaks out into the surrounding tissue, causing swelling. This isn't a malfunction, it's a strategy. The increased blood flow delivers an army of immune cells to the breach. The heat creates an environment where bacteria struggle to reproduce. And the swelling? That's just collateral damage. The first responders arrive in minutes. Neutrophils. These are white blood cells that exist for one purpose: find invaders, eat them, and die. They make up about 50 to 70% of all your white blood cells, and your bone marrow produces billions of them every single day. Neutrophils move through your bloodstream until they reach the site of the cut. Then they squeeze between the cells lining your blood vessels and enter the tissue. Once there, they start hunting. When a neutrophil encounters a bacterium, it engulfs it whole in a process called phagocytosis, literally, cell eating. The neutrophil wraps itself around the bacterium, pulls it inside, and then floods it with toxic chemicals that break it down. But here's the thing. This process destroys the neutrophil too. After a neutrophil eats a few bacteria, it dies. The average lifespan of a neutrophil at an infection site is only a few hours. Right behind the neutrophils come the macrophages. These are the cleanup crew. Macrophages are bigger, tougher, and they live longer. They eat bacteria, sure, but they also eat dead neutrophils, damaged tissue, and any other debris left behind from the battle. And that gross yellow stuff you see oozing out of an infected cut, pus, that's what's left after the war. Dead neutrophils, dead bacteria, tissue debris, and fluid all mixed together. It's disgusting, but it's also proof that your immune system is doing its job. This entire response happens in the first 4 to 6 hours after injury. For most minor cuts and scrapes, it's enough. The neutrophils and macrophages show up, kill the invaders, clean up the mess, and you never even notice. This happens thousands of times in your life for every tiny scratch, every splinter, every irritation you barely register. But neutrophils and macrophages are generalists. They attack anything foreign. What happens when the infection is too weird, too fast, or too strong for them to handle alone? Sometimes the invader is too smart for the first responders. A flu virus, salmonella from undercooked chicken, something your neutrophils can't just eat and forget about. So how does your body learn what it's actually fighting? Enter the dendritic cells. These are the intelligence officers of your immune system. When an infection gets serious, dendritic cells travel to the site, grab samples of the pathogen, and rush them back to headquarters, your lymph nodes. You've probably felt swollen lymph nodes before. When you're sick and you feel those tender lumps in your neck, armpits, or groin, that's not infection. That's your immune system's training center working overtime. Inside those lymph nodes, dendritic cells are presenting pathogen samples to millions of other immune cells, essentially showing them what the enemy looks like. But here's the problem. This takes time. Your adaptive immune system, the specialized response that targets specific pathogens, needs 3 to 7 days to fully activate. That's why you feel worst on days 3, 4, and 5 of an illness. The war is escalating. Your body is ramping up production of specialized weapons, but they're not ready yet. In the meantime, your body tries to slow down the invader using a blunt instrument, fever. When you're sick, your brain deliberately raises your body temperature. A normal temperature is 98.6 degrees Fahrenheit. During an infection, your body might push it to 101, 102, even 103 degrees. That sounds like a malfunction, but it's not. Most bacteria and viruses replicate best at normal body temperature. Raise the temp by even 2 degrees, and their reproduction rate slows down significantly. It's like forcing the enemy to fight in extreme heat. They're still dangerous, but they're weakened. Meanwhile, your immune cells actually work better at slightly higher temperatures. So a fever isn't your body breaking down, it's your body buying time. And that's also why you feel exhausted when you're sick. Your immune response burns calories like a workout. Some estimates suggest that fighting an infection can burn an extra 400 calories per day or more. Your body is diverting massive amounts of energy away from normal functions and toward the immune response. That's why you lose your appetite, why you feel weak, why all you want to do is sleep. During this waiting period, your lymph nodes are working non-stop. Dendritic cells are showing pathogen samples to T cells and B cells, trying to find the ones that can recognize this specific invader. It's like searching through millions of keys to find the one that fits a particular lock. Once the right cells are found, they need to multiply. 1 cell becomes 2, 2 become 4, 4 become 8. This clonal expansion takes days. But once it happens, the real specialized killers enter the fight, and they're terrifyingly precise. Meet the T cells, the Navy SEALs of your immune system. They don't just kill invaders, they kill your own cells that have been infected, and sometimes that's exactly what needs to happen. Here's the problem. Viruses don't just float around in your bloodstream, waiting to be eaten by neutrophils. They hijack your cells. A virus injects its genetic material into one of your cells, takes over the machinery inside, and forces that cell to make thousands of copies of the virus. It's like a factory being seized by an enemy and converted to produce weapons. Your infected cell knows something's wrong. So, it does something remarkable. It takes fragments of the viral proteins being produced inside it, and displays them on its surface. It's like waving a red flag that says, "I've been compromised. Kill me before I make more viruses." That's where killer T cells come in. These cells patrol your bloodstream constantly, checking every cell's ID badge. Each cell in your body displays proteins on its surface that essentially say, "I'm part of you, don't attack me." But if a cell is infected, it displays viral proteins alongside the normal ones. And killer T cells are trained to recognize that. When a killer T cell finds an infected cell, it doesn't hesitate. It attaches to the infected cell and injects a protein that triggers apoptosis, controlled cell death. The infected cell essentially commits suicide, breaking itself down from the inside in about 30 minutes. The cell dies before it can produce more viruses, and the debris gets cleaned up by macrophages. This is happening constantly. During a flu infection, billions of T cells are activated, scanning billions of cells, looking for that red flag. Most cells pass inspection, but the infected ones, they get a death sentence. Now, killer T cells are the executioners, but they don't work alone. Helper T cells are the coordinators. They release chemical signals called cytokines that recruit more immune cells to the fight, amp up the response, and tell your B cells to start making antibodies. Without helper T cells, your immune system can't organize a proper defense. And that's why HIV is so devastating. HIV specifically targets and destroys helper T cells. The virus attacks the very cells that coordinate your immune response. Your body tracks this with something called a CD4 count, which measures how many helper T cells you have. A healthy person has 500 to 1,500 CD4 cells per microliter of blood. When HIV drives that number below 200, you're diagnosed with AIDS. At that point, your immune system can't coordinate defenses anymore, and infections that would normally be minor become life-threatening. But when the system works, it's brutally effective. One infected cell can produce 10,000 virus copies in 24 hours if left alone. But if killer T cells find it early, they stop the spread before it starts. It's precision execution on a microscopic scale. And yet, T cells can't do it alone. They need backup. Enter the assassins with photographic memory, B cells, and antibodies. Antibodies are the most elegant weapons in biology. Y-shaped proteins, each one custom designed to lock onto one specific invader. And your body can make billions of unique antibody types. Pretty crazy. These antibodies come from B cells, which are basically protein factories sitting in your lymph nodes. When a B cell encounters a pathogen that matches its particular antibody design, it goes into overdrive. It starts pumping out thousands of copies of that antibody into your bloodstream. Here's how they work. Each antibody has two binding sites at the top of the Y shape. These sites are designed to attach to specific proteins on the surface of a pathogen. It's a lock and key mechanism. One antibody type fits one pathogen protein and nothing else. When an antibody binds to a virus or bacterium, it essentially tags it for destruction. It's like spray painting, "Kill me," on the invader in bright fluorescent colors. Once tagged, the pathogen is neutralized. Antibodies can prevent viruses from entering your cells by blocking the proteins the virus uses to attach. They can clump bacteria together, making them easier targets for macrophages to eat. And they can directly mark pathogens for destruction by other immune cells. Even a single antibody binding to a virus can be enough to stop it. But here's where it gets really impressive. Your body doesn't know in advance which pathogens you'll encounter, so it creates billions of different B cells, each one programmed to make a slightly different antibody. It's like having billions of different keys ready, waiting to find out which locks exist in the world. When the right B cell finds its matching pathogen, it undergoes something called clonal expansion. One B cell becomes 2, 2 become 4, 4 become 8. Within days, that single B cell has produced thousands of identical copies of itself, all pumping out the same antibody. During peak production, your body can generate billions of antibodies per day. There are different types of antibodies for different jobs. IgM antibodies are the first responders, appearing within days of infection. They're big and clunky, but effective. IgG antibodies come next, and these are the long-term defenders. They're smaller, more efficient, and they stick around in your bloodstream for months or even years. IgA antibodies patrol your mucous membranes, guarding your nose, throat, and gut. And IgE antibodies are involved in allergic reactions, though that's a whole other story. The timeline matters. It takes about 7 to 10 days from the start of an infection for antibody production to hit its peak. That's why you start feeling better around day 7 or 8 of a cold or flu. The antibodies have finally arrived in force, and they're mopping up the remaining viruses. This precision is what makes antibodies so powerful. They don't just attack randomly. They target specific molecular structures on specific pathogens with surgical accuracy. But this targeting system is so precise that it's supposed to ignore your own cells completely. The problem is, sometimes it doesn't, and that's when your immune system becomes your worst enemy. Everything we've talked about so far assumes your immune system knows enemy from friend. In about 5 to 8% of people, it doesn't. And that's when things go horribly wrong. Autoimmune disease. That's what happens when T cells or antibodies mistake your body's own proteins for enemy targets. The precision weapons we just talked about, they turn inward, and the results can be devastating. Take type 1 diabetes. Your immune system decides that the insulin-producing cells in your pancreas are the enemy. T cells attack and destroy them. Without insulin, your body can't regulate blood sugar, and you're dependent on insulin injections for the rest of your life. The system designed to protect you just destroyed a critical organ function, or rheumatoid arthritis. Your immune system attacks the tissue lining your joints. The inflammation that's supposed to fight infection, it never stops. Your joints swell, ache, and eventually deteriorate. The chronic inflammation can be so severe that it deforms the joints permanently. Multiple sclerosis works differently. Your immune system attacks the myelin sheath, which is the protective coating around your nerve fibers. It's like stripping the insulation off electrical wires. Nerve signals get disrupted, leading to problems with movement, vision, and coordination. Over time, the damage can be irreversible. Then there's lupus, where your immune system can attack multiple organs at once: skin, joints, kidneys, heart, lungs. In some cases, antibodies even target your own DNA. The disease can flare up unpredictably, causing severe inflammation throughout your body. Why does this happen? We don't fully understand it. There's usually a genetic component, which means some people are predisposed to autoimmune diseases. But genes alone aren't enough. Something triggers the system to go haywire. Maybe an infection where the pathogen's proteins look similar to your own proteins, confusing your immune system. Maybe environmental factors, stress, or other unknowns. Scientists are still trying to figure it out. And here's the cruel irony. Women get autoimmune diseases 2 to 3 times more often than men. Nobody knows why. It might be related to hormones, or the way the female immune system is slightly more aggressive to protect pregnancy, or something else entirely. Treatment is complicated. Immunosuppressants can dial down the immune response, which reduces the inflammation and slows the damage. But lowering your immune response means you're more vulnerable to real infections. It's a constant balancing act. Suppress the system enough to stop it from attacking you, but not so much that you can't fight off bacteria or viruses. That's genuinely awful. The system that's supposed to save your life becomes the thing actively trying to destroy it. And for millions of people living with autoimmune diseases, this isn't a hypothetical scenario. It's daily reality. Your body at war with itself, inflammation that never ends, organs under constant attack from the very cells meant to protect them. But here's the flip side. If we can train your immune system to attack the right targets, we can prevent diseases before they start. And that's exactly what vaccines do. Why don't you get chickenpox twice? Because your immune system has a photographic memory. Here's how it works. After your body fights off an infection, some of those B cells and T cells don't just disappear. They become memory cells. These cells stick around for years, sometimes decades, patrolling your bloodstream and lymph nodes. They're programmed to recognize one specific pathogen, and they never forget. When you're exposed to the same pathogen a second time, these memory cells activate in hours instead of days. They immediately start producing antibodies and coordinating an immune response. The invader gets destroyed before you even feel sick. That's why you can be exposed to chickenpox as an adult and not get it again. Your memory cells recognize it instantly and shut it down. But not all immunity lasts forever. Some memory cells die off slowly over time. Measles immunity? That can last a lifetime. But flu immunity? That fades within months. The memory cells for influenza don't survive as long, which is why you can get the flu multiple years in a row. This is where vaccines come in. A vaccine gives your body a harmless version of a pathogen. Sometimes it's a dead virus, sometimes it's a weakened one that can't cause disease, and sometimes it's just a fragment of the pathogen, like a single protein. Your immune system sees this fake threat and mounts a full response. Dendritic cells gather samples. T cells activate. B cells produce antibodies. The whole system kicks into gear. But here's the brilliant part. You never actually get sick. The pathogen can't replicate or cause damage. Your body just practices fighting it. And when the response is over, you're left with memory cells that recognize the real pathogen if you ever encounter it. That's why you need booster shots for some vaccines. The memory cell population fades over time, so a booster gives your immune system a refresher. Take COVID, for example. The original vaccines required multiple doses because immunity faded relatively quickly. And when new variants like Omicron emerged with mutations that changed the spike protein, some of the memory cells didn't recognize it anymore. The virus had essentially changed its disguise. Different vaccines use different strategies. mRNA vaccines give your cells instructions to make a specific viral protein. Live attenuated vaccines use weakened versions of the actual virus. Protein subunit vaccines deliver just a piece of the pathogen, but they all have the same goal: create memory cells without making you sick. The timeline is important. After vaccination, it takes about 2 weeks for your body to build up a strong memory cell population. That's why you're not fully protected immediately after getting vaccinated. So, that's the system. From barrier breaches to cellular warfare to decades-long memory. And all of this is happening in your body right now, while you're just sitting there. Right now, as you finish reading this, your body just killed about 10 million bacteria. You didn't feel any of it. This war never stops. Every single day, your bone marrow produces billions of new immune cells, neutrophils, macrophages, T cells, B cells, all constantly being manufactured and deployed. Millions of pathogens are eliminated before they can cause harm, and you're completely unaware of any of it. Think about what life was like before modern medicine. Before antibiotics were discovered in the 1920s, the average human lifespan was around 40 years. Infections killed most people. A simple cut could lead to sepsis. Pneumonia was often a death sentence. Childbirth was incredibly dangerous because of infection risk. Your immune system was all you had, and for many people, it wasn't enough. Today, we have antibiotics, antivirals, and vaccines as backup. But here's the thing. Your immune system still does 99% of the work. Medicine just tips the scales in close battles. Antibiotics weaken bacteria so your immune cells can finish them off more easily. Antivirals slow down viral replication, giving your T cells and antibodies time to catch up. Vaccines train your memory cells so they're ready before the battle even starts. Without your immune system, all the medicine in the world wouldn't save you. That's what happens to people with severe immunodeficiency. Even with the best medical care, they struggle to survive. Let's put some numbers on this. In the United States alone, antibiotics save an estimated 200,000 lives every year. Vaccines prevent millions of infections annually. But your immune system? It prevents billions of infections every single day across the entire human population. The scale is incomprehensible. Remember those neutrophils that arrive within minutes of a cut? They're dying for you constantly. Remember the T cells scanning billions of cells looking for infection? They're working right now. The B cells producing antibodies, the macrophages cleaning up debris, the memory cells standing guard against pathogens you encountered years ago. All of it is happening automatically. Every fever you've ever had, every swollen lymph node, every moment of exhaustion during illness, that wasn't weakness. That was evidence of war. Your body redirecting massive amounts of energy toward survival, fighting battles you couldn't see. And by the way, your appendix might actually be a safe house for good bacteria. Scientists are still figuring that out. Turns out the organ we thought was useless might actually help repopulate your gut with beneficial microbes after an infection wipes them out. Pretty crazy that all this happens automatically, without you thinking about it once. Your body is at war right now, and it's